Well, welcome back to our course on discrete mathematics, CS 160, discrete structures. And this particular lecture, we're going to have our first discussion for chapter 1. And this is actually complicated enough material that we're going to have 3 different lectures that we're going to talk about it. And even still, there's going to be a lot of information in each one of these. So what we're going to explain in this chapter is what makes up a correct mathematical argument and introduce tools to construct these arguments. We will develop an arsenal of different proof methods that will enable us to prove many different types of results. After introducing many different methods of proof, we will introduce several strategies for constructing proofs, and we'll introduce the notion of a conjecture and explain the process of developing mathematics by studying conjectures. And so there's a lot of material, and we're going to be getting familiar with how Rosen does his book. There's you can tell that he's really enthused by this material in multiple ways. And so I'll just have that as a little bit of introduction for now. So I'll first talk about the whole chapter, but this lecture is going to be focusing on the first part, which is going to be propositional logic. And so these are the 3 things that the whole chapter talks about. So for propositional logic, the rules of logic specify the meaning of mathematical statements. So for instance, these rules help us to understand and reason with statements such as there exists an integer that is not the sum of 2 squares, and for every positive integer n, the sum of the positive integers not exceeding is n times the quantity n plus 1 divided by 2. Logic is the basis of all mathematical reasoning and of all automated reasoning. So we can see mathematics and computer science play both into that. It has practical applications to the design of computing machines, to the specification of machines, to artificial intelligence, to computer programming, to programming languages, and to other areas of computer science, as we'll get exposed to some of that in this course. Okay, the next thing is predicate logic. You can think about this how we use qualifiers. So to understand mathematics, we must understand what makes up a correct mathematical argument that is a proof. Once we prove a mathematical statement is true, we call it a theorem. A collection of theorems on a topic is topic organize what we know about this topic. And to learn a mathematical topic, a person needs to actively construct mathematical arguments. And so that's some of what we're going to get a chance to be thinking about, that constructing arguments on a particular topic and not just read exposition. Moreover, knowing the proof of a theorem often makes it possible to modify the results to fit to a new situation. And then thinking a little bit more about proofs, everyone knows that proofs are important throughout mathematics, but many people find it surprising how important proofs are in computer science. In fact, proofs are used to verify that computer programs produce the correct output for all possible input values, to show the algorithm always produce the correct results, to establish the security of a system, and to create artificial intelligence. Furthermore, automated reasoning systems have been created to allow computers to construct their own proof. So in this chapter, we will explain what makes up a correct mathematical argument and introduce tools to construct these arguments. We will develop an arsenal of different proof methods that will enable us to prove many different types of results. After introducing many different methods of proofs, we will introduce several strategies for constructing proofs. We will introduce a notion of a conjecture and explain the process of developing mathematics by studying conjectures. So there's a lot of material here, and we'll try to keep it at a high level, but just keep that in mind. You may want to pause it periodically and review what we covered. So now instead of just looking at the whole chapter, we're just looking for this first section here, talking about propositional logic. So our discussion begins with an introduction to the basic building blocks of logic, that is, propositions. A proposition is a declarative sentence, that is a sentence that declares a fact that is either true or false, but not both. So we need to be thinking about how we determine those truth values, and then we'll be showing you examples of truth tables. In terms of applications, logic has many important applications in mathematics, computer science, and numerous other disciplines. Statements in mathematics and the sciences and in natural languages often are imprecise or ambiguous. That can be a problem. So to make such statements precise, they can be transitioned into the language of logic. So for example, logic is used in the specification of software and hardware because these specifications need to be precise before development begins. Furthermore, propositional logic and its rules can be used to design computer circuits, to construct computer programs, and to verify the correctness of programs, and to build expert systems. Logic can be used to analyze and solve many familiar puzzles. Software systems based on the rules of logic have been developed for constructing some, but not all types of proofs automatically. And we'll discuss some of these applications of propositional logic in a section later, and so keep that in mind. Then we have equivalences. An important type of step used in mathematical arguments is the replacement of a statement with another statement with the same truth value. Because of this method, that produces propositions with the same truth value as a given compound propositions are used extensively in the construction of mathematical arguments. Okay, well, let's get into those three elements for this lecture, the first being propositional logic. So here are the kind of things that we're going to be talking about. We'll introduce some examples of propositions, and then we'll talk about connectives. And so depending on your background, I have an engineering background and computer science, but the terms that I'm more familiar with are using things like this. So negation not would be the term that would be one that I would utilize most. And we'll see examples of how that starts to play out in parts of our course. A conjunction would be what I would say you could use the term or for that. Disjunction is and, so or means one or both of them needs to be true for the output to be true, and means both have to be true. And then we have these other things here: implication, contrapositive, inverse, converse, and biconditional. And so I put in some extra information here that might be helpful. The implication statement, if P then Q, asserts Q is true on the condition that P holds. Contrapositive of if P then Q is a proposition not Q, then not P. The proposition not P, then not Q is called the inverse of P then Q. The proposition Q, if Q then P, is called the converse of if P then Q. And the biconditional statement is, as we're shown here, is a proposition if and only if Q. And so these are some of the things that we're going to be leveraging as we start to look at how to put these things into propositions. So a proposition is a declarative statement that is either true or false. And so we'll have examples of ones that are proposition, ones that aren't. So ones that are: the moon is made of green cheese, the Trenton is the capital of New Jersey, Toronto is the capital of Canada, 1 + 0 is 1, and 0 + 2 = 2. And it kind of depends on what we're talking about. If these are numbers or if they're entities, and so there's two entities here, and then so we can say that that's we can think of a way that that's true, or it is false, and 0 plus 0 is not. It depends on what we're talking about. And then definitely ones that are not propositions, sit down. What time is it? X plus 1 equals 2. X plus Y equals Z. Those are not propositions. And so these are not true or false. And so those are the things we're trying to avoid when we're dealing with propositions. So for constructing propositions, we have variables, things like P, Q, R, S. The proposition that is always true is denoted by T, and the proposition that is always false is denoted by F. And then we can have compound propositions constructed from logic, connectiveness, and other propositions. And I mentioned those already, but just as a reminder, here are example of ones that are going to be common that we're going to be exposed to. Well, let's get into more details of what these are. We'll also show some examples of truth tables, and so the negation or not. And so the proposition P is denoted by not P, and it has this truth table. So here we're showing P if it's true. If we have not P, then it's going to be false. And so if P is false, then not P is true. And so if P denotes the earth is round, then not P denotes it is not the case that the earth is round, or more simply saying that the earth is not round. Once again, this operative word that I like to remember is not. For conjunction, or the way I'm used to thinking of it is just thinking of an and so it's a conjunction of two propositions P and Q, and so we have this annotation that how we write that in terms of the logic descriptors, and it has this truth table. The only time that is true if P and Q are true, and then the output would be true. So if P denotes I am at home and Q denotes it is raining, then P and Q denotes I am at home and it is raining. And so I'll tend to use the word and for this descriptor. Disjunction or, the disjunction of propositions P and Q is denoted by P or Q and has this truth table. And it is always going to be true if one or both of them are true, and the only time it is false is when both of them are false. So if P denotes I am at home and Q denotes it is raining, then P or Q denotes I am at home or it is raining. Well, we can get into more interesting ways of looking at or, and so you can either have an inclusive or, and so that's what we saw previously, or the exclusive or. The exclusive or has this type of descriptor, and it's listed here, and it means that if one of them is true, then it's true. Otherwise, if both of them are true or both of them are false, that's going to give a false output. And so this is the truth table for that, and you can see the examples. I won't read through those here, but just let you go ahead and pause the video and you can review that. Or of course, the textbook is the best source to get this in context. Then we have the implication. If P and Q are propositions, then if P, then Q is a conditional statement or implication, which is read, as I said, if P, then Q, and it has this truth table. So basically, if they're both true, then it's going to give the implication is going to be true. Or if they're both false, it's going to give the output as being true. So those are two of the cases that we have here. We also have if P, which is false, leads to Q, which is true, then that's also going to be true. But the case that if it's true and then the output is Q, so if P, which is true, then Q, which is false, that will give a false output. So if P denotes I'm at home and Q denotes it is raining, then Q denotes if I am home, then it is raining. Okay. So that just gives you another thing that we'll be using in our logic statements as we put these things together. If P then Q does not need to be in any connection between the antecedent or the consequence, the meaning of if P then Q depends only on the truth table P and Q. These implications are perfectly fine, but would not be used in ordinary English. If the moon is made of green cheese, then I have more money than Bill Gates. The moon is made of green cheese and I'm on welfare. If 1 + 1 = 3, then your grandma wears combat boots. And so you can be thinking about those. On one way to view the logical conditional is to think of an obligation or contract. If I am elected, then I will lower taxes. If you get 100% of the final, then you will get an A. If the politician is elected and does not lower taxes, then the voter says that he has or she has broken the campaign pledge. And something similar holds for professor. This corresponds to the case when P is true and Q is false. And so thus you can be using some of these implications, the truth table we showed there, to have you be thinking about those in a little bit more detail. We have the converse, the contrapositive, and inverse. So from if P then Q, we can form these new conditional statements. You can inverse it, and so that's the converse. You can negate both sides, and that's a contrapositive. You can negate both sides of the inverse and the converse and get the inverse. And so those are all things that are there. So find the converse, inverse, and contrapositive. If it is raining, is a sufficient condition for mine not going to town. So the converse, if I do not go to town, then it is raining. Inverse it, if it is not raining, that I will not go to town. And the contrapositive, if I go to town, then it is not raining. So those are some examples that you can be thinking about. Well, what about this biconditional? If P and Q are propositions, then we can form the biconditional proposition here. P if and only if Q, and so the biconditional way of writing it here denotes this proposition with a truth table before. And so for this case, we have it, both of them have to be true or both of them has to be false to give a true at the output. And so you can be thinking about that and comparing it to what we saw for the imperative. Let me just go back a couple slides just to remind you of that. The implication. And so we have that. There's three cases where it's true, one where it's negative, negative or false. Here we can see there's only the case when they're both true or both false does it give a true satisfaction of the biconditional. So thus, if P denotes I'm at home and Q denotes it is raining, then if and only if scenario that we have with a biconditional denotes I am at home, if and only if it is raining. Some alternative ways to state P if and only if Q is to express P is necessary and sufficient for Q, if P then Q, and conversely, and P if Q. So those are some things in English that you might get a chance to be exposed to. What about truth tables for compound propositions? And so we're going to be now stitching some of these things together. Doing algebraic equations, if you will. So for the construction of a truth table, the rows, you need a row for every possible combination of values for the atomic propositions. And so this is the term I haven't talked about yet. Propositions that cannot be expressed in terms of simpler propositions are called atomic propositions. For the column, you need a column for the compound proposition, usually at the far right. And you need a column for the truth value of each expression that occurs in a compound proposition and is built up. And so this includes the atomic proposition. Okay, so here we can see that we have these things individually, the propositions, Then we have, I'm just going to call the negation. And then we have these other ones that are added to till we finally get to the output, what is the final state that we're looking for. And so this is an example of a complicated truth table that's putting multiple of these things that we've been introduced so far together. Another thing that is helpful is to be thinking about equivalent propositions too. So two propositions are equivalent if they always have the same truth value. So an example is show that a truth table that the conditional is equivalent to the contrapositive. And so thus we can see by building these things up, we can see that these two examples here, the conditional and the contrapositive are the same. And so we can see that that's a way that we can show that there is an equivalence between those. And so that's valuable. You can also use a truth table to show non-equivalence. And so here we're going to show that the truth table that neither the converse nor inverse of an implication are not equivalent to the implication. So we have the implication and then we have these other two ones. And here's an example, the one part of it that doesn't show as being the same. And so therefore they're not equivalent. And so thus we've demonstrated that we can see that being laid out there. So how many rows are there in a truth table with n propositional variables? You can be thinking about that. I'll just go ahead and walk through this. The solution is 2 to the n. We will see how to do this later in chapter 6, but this is a little bit of a preview for what's going to be coming up. Note that this means that n propositional variables, we construct 2 to the n distinct, that it is non-equivalent propositions. Okay, another thing that we have to be thinking about is the precedence of operators. And so here, for all of these different operators we've been exposed to, here is a precedence. So the inversion has the highest precedence among these 5 things there. And so as a result, just as we would have when we're doing multiplication, division, addition, subtraction, and exponentiation and everything that we would have a precedence, we have it for these operators as well. We can override those precedences by using parentheses. And so that's another thing that we will be getting some insight into using as we go forward. Okay, now let's get into the second part of this first lecture, where we talk about the applications of propositional logic. So here are the things that we're going to be looking at, translating English to propositional logic, system specifications, Boolean searching, logic puzzles, and logic circuits. And we'll at least talk about this a little bit, artificial intelligence diagnostic method. And so this is the first chapter that we're covering, but hopefully you're going to see an increasing trend where we're going to be trying to show some practical applications. And Rosen also tries to make it a fun experience. And so hopefully as you get more and more into his material, you'll get a chance to have an enjoyable response. And maybe you'll find certain things here that you really enjoy and you might want to continue to press forward with. So how do we go about translating English sentences? So the steps to convert an English sentence to a statement in propositional logic are to identify atomic propositions and represent using propositional variables. And so we've gotten familiar with what those are, determine appropriate logical connectives. And so if I go to Harry or to the country, I will not go shopping. And so you can see there's 3 things: go to Harry's, go to the country, and I will go shopping. And so we label those as P, Q, and R. And so if P or Q, then not R, this is how we can be putting that into propositional logic. And so hopefully that makes sense based on the material that we've covered up to this point. So here's an example. So a problem: translate the following sentence into propositional logic. You can access the internet from campus only if you are a computer science major or you are not a freshman. So one solution is let A, C, and F represent respectively. So you can access the internet from campus. C, you are a computer science major, and F, you are a freshman. So I tried to label those in color to give you a little bit of an idea of that. And so here would be how we could be putting that into propositional logic. So hopefully, as we get through this material, you can maybe get more familiar with this, try some examples. Rosen has tons of exercises and samples, and so I'm sure that you'll find plenty of information to help you get more familiar with how this works. Next, looking at system specifications. Systems and software engineers takes requirements in English and express them in a precise specification language based on logic. Really an important area to be dealing with requirements. Some examples of expression in proposition logic: the automated reply cannot be sent when the file system is full. And so a solution is, one possible solution is let P denote the automated reply can be sent, and Q denote the file system is full. And so thus we can see a propositional expression, how that could come together as we're showing here. Okay. Then we have consistent system specification, a definition. A list of propositions is consistent if it is possible to assign truth values to the proposition variables so that each proposition is true. And in terms of an exercise, are these specifications consistent? The diagnostic message is stored in the buffer or is retransmitted. The diagnostic message is stored in the buffer. And if the diagnostic message is stored in the buffer, then it is retransmitted. And the answer is, so let P denote the diagnostic message is stored in the buffer. Let Q denote the diagnostic message is retransmitted. And so thus the specification could be expressed in this kind of a format. So when P is false and Q is true, all three statements are true, so the specification is consistent. Well, what if we did a slight change here? What if the diagnostic message is not retransmitted is added? Then solutions, now we've added not Q, and there is no satisfying assignment, so the specification is not consistent. So like I said, feel free to pause the video or look in Rosen in the textbook, and you can get a chance to be thinking about this in more detail. Well, this is the first time that has come up, and sometimes, but not always, I will be referring to the mathematician that Rosen talks about. This is another really neat feature. To think about some of the things that we're being exposed to. Sometimes this is like the things that these mathematicians worked on for decades to come up with these results. And in this textbook, we have quite a few mathematicians that we've looking at those results, synthesizing them and applying them. So we're like standing on the shoulders of mathematicians. And so that's a really great thing that we're able to use. So let's think about logic puzzles. An island has two kinds of inhabitants: knights who always tell the truth and knaves who always lie. So do you go to an island and meet A and B? A says B is a knight, and B says that the two of us are the opposite types. What are the two types of A and B? And so how would we go about solving that? So let P and Q be the statements that A is a knight and B is a knight respectively. So then not P represents a proposition that A is a knave, and not Q that B is a knave. So if A is a knight, then P is true, since knights tell the truth, and Q must also be true. Then we have this expression that's laid out there. Sorry, it's scrolled over to the next line, but I think you're catching it. Would have to be true, but it is not. So A is not a knight, and therefore not P must be true. If A is a knave, then B must be a knight, since knaves always lie, so that both not P and not Q hold, since both are knaves. So you can see that there's a logical way that we're starting to get a chance to be figuring about how to go about solving a problem. We're going to be getting into logic circuits in depth in chapter 12, but we're getting a preview of this. And if some of you who are watching this video have some engineering background, you may have been exposed to these. And so these are what I have had a lot of experience with. And so the inverter, I like to use the word not. I've already used that term, or it can be that either one of these inputs will give a true on the output. And you can see it's a little bit small here, but you can see the way it's written in logic. A downtick, an uptick. And so and is for a true output, both of them have to be true on the input. This is an inverter, so it's opposite of the input. So this is pretty interesting for us to be thinking about it, but we can have these complicated digital circuits can be constructed by combining these basic circuits to produce the desired output, given the input signals by building a circuit for each piece of the output expression and then combining them. So here is an example, and you can see that we have this kind of an expression, and I'll just go back a few charts. And so sorry for, I'll try not to do this too much here, but we had an example of these kind of complicated statements here. Basically, we could build this into a circuit like what I'm showing here. And so thus, say if you had an Arduino unit or just a logic board that you put these gates together, you could actually produce this automaton that would do, based on the truth or falseness of these three inputs, you can get this result. So that's actually a pretty novel thing that's there. It's used in computer architectures. It's used in electronics. It's used for control systems. There's a lot of different things that start to come out there. This next one, I will go through a little bit quickly, but just think of what we did with this logic circuit. And this is like getting a chance to be thinking about something more in depth. And so a diagnostic of a faults in an electrical system. And so this is an artificial intelligence example from Artificial Intelligence Foundations of Computational Agents by David Poole and Alan Mackworth, 2010. You need to represent in propositional logic the features of a piece of machinery or circuits that are required for the operation to produce observable features. This is called the knowledge base. We also have observations that represent the features that the system is exhibiting now. So this, you can see an example that you have wires, you have lights, you have switches, and a circuit breaker. And so we created a schematic of what it looks like for putting all of those things together. And this is the next page, gives the knowledge base for describing the circuits and the circuit observations. I'm not going to go through this in detail, but what we've done is we've taken the desired performance and to put it into propositional logic. And just thinking about this circuit here, you can actually have a circuit that takes this type of input and codifies it, so it's going to produce those results every time. And so that is actually a fairly novel thing. So I'm not going to go through this. This is some more supporting details, but this is more of the knowledge base that's associated with how this all comes together. And you can see that, relatively speaking, maybe this is still not that complicated, but you can see that there's a lot of knowledge base information that we want to capture there. So the observations need to be added to the knowledge base, and these are some things that are suggested. and I'll just refer you to Rosen and the textbook to go through that in more detail. So just a quick takeaway, we have an example that I showed for a simple circuit here that you can put things into logic. We then had an example of hardware, not necessarily logic gates, that we can be applying propositions and capture all of that into a knowledge base that is basically how all this is supposed to be programmed, make some observations, maybe things need to be added, maybe they don't, or we can start to troubleshoot it and make sure it's performing it as desired. So that's something that I think that you will get exposed to in the future, at least some of you, depending on what particular area of engineering, computer science, or mathematics that you get into. So we assume that the components are working okay unless we are forced to assume otherwise. And these atoms are called assumables. And so here we have some things that are laid out here. If the system is working correctly, all the assumables are true, the observations and the knowledge base are consistent, so that is, it's satisfiable. The argumented knowledge base is clearly not consistent with the assumables are all true. The switches are both up, but the lights are not lit. Some of the assumables must be false. This is the basis for the method to diagnose possible faults in the system. A diagnosis is a minimal set of assumables which must be false to explain the observations of the system. So we can have like some kind of a circuit, something that we're working on. We figure out how we're going to be programming that. We have all of these things in our propositional format. And now we start to do some diagnostics to see if it's functioning okay. And you could refer back to this textbook to be getting some more details about this. And here is an example. The approach yields 7 possible faults in the system. So these would be situations that you would want to have a notification that something is not proper in the system and that the operator should be notified. Okay, so that's a little bit of giving you some insight of how you can be using some of this propositions, taking English, putting it into propositional logic, taking that propositional logic, and you can actually build it into hardware. Okay, this third and last part for this lecture, we will be talking about propositional equivalences. And so here are the things that we'll be talking about here. And we'll have some examples. Note that there is going to be some things in the textbook that are not going to be covered in these lectures. And so I have it here, optional. It's covered in the exercises in text. And so we won't necessarily cover everything that's in the textbook. So that is another thing that will happen. And so if some of you likes puzzles, here is an example of a puzzle that maybe some of you have tried, and we'll start to get into that and be thinking about how we would be looking at that. So here are a couple of definitions, different types of propositions. So here's the first one. Tautology is a proposition which is always true. A contradiction of proposition which is always false. And a contingency is a proposition which is neither a tautology nor a contradiction. And so we're seeing some things that are laid out here, what we can be doing to P to be showing these 3 classifications of things that we may want to be utilizing. Logically equivalent. 2 compound propositions P and Q are logically equivalent if we have this kind of relationship. So P and Q is a tautology. So we have a couple different ways of writing those. You have used one or the other. So they're equivalent would be the triple lines there. Maybe you've seen that before, where P and Q are compound propositions. The two compound propositions P and Q are equivalent if and only if the columns in the truth table given their truth values agree. So you could say this is a form of proof, and we had a chance to be thinking about this a little bit already. And we can see that since these truth table are equivalent, thus we can say that these that since all of the truth tables have the same values, then they're equivalent, and we've proven that. Here is De Morgan's law, and so these just give you a proof for that. A fairly straightforward way of to be thinking about that. And so basically we have these two cases here that are laid out, and we can see that they get to the same values. And so we've been able to prove that they're true. Once again, I will refer you to Rosen in the textbook to be thinking about that in more detail. There will be examples of charts like this where they give you some equations, things that you would have like in a reference book. And I won't go over these in detail, but identity laws, domination laws, idempotent laws, double negation law, and negation laws. These are all things that could be helpful. So basically, we're getting a lot of tools in propositional logic similar to algebra that we can be using to be solving expressions, to be creating expressions, and then trying to simplify them. These are all the things that are possible. Here are some other key logical equivalences: accumulative laws, associative laws, distributive laws, and absorption laws. Once again, like I said already, I'm not going to go through those in detail. You can pause the video or look in Rosen and get a chance to be seen about those. Here are just some more equivalences, logical equivalences involving conditional statements, and logical equivalences involving biconditional statements, which are things that we've already covered at this point. We can get into constructing new logical equivalences. We can show that two expressions are logically equivalent by developing a series of logical equivalent statements. So to prove that A is equivalent to B, we produce a series of equivalences beginning with A and ending with B. And so here we can be seeing something like that. Keep in mind that whenever a proposition represented by a propositional variable occurs in the equivalences listed earlier, it may be replaced by an arbitrary complex compound proposition. So I won't tend to go through proofs. And so basically what we're showing that this expression is equivalent to that. Here is a proof. Rosen has it in the textbook and in detail. And you could pause the video and see this, but I'm just going to go skip over that and just say that this equivalence is something that we can count on. And we can see how we're using different things. We briefly mentioned De Morgan's law. We have the double negation. And so thus we're using different type of things that we've used in our handy dandy equivalences to help us to come up with this solution, go from one to the other. So here's another example where we're showing that this is a tautology. And here are the steps that we go about doing that. Some of this optional material, I'm just going to quickly go over this, but there will be some of these stuff that I'll just leave. And so a propositional formula is a disjunctive normal is in disjunctive normal form if it consists of a disjunction of what's listed there. Disjuncts with each disjunct consists of a conjunction that's listed there, atomic formula, or the negative of the atomic formula. And so disjunctive normal forms is important for the circuit design method discussed in chapter 12. And we'll begin into chapter 12. I think I will be able to give a little bit better context for this. Maybe not exactly thinking it from this point of view. This is definitely a heavily mathematical way of thinking about circuit development, but let's just keep us aware of that. And so here's an example, show that every compound proposition can be put in disjunctive normal form. I'll leave this up to you that you can go look over that and think about it. Constructing the truth table from the proposition, then an equivalent proposition is the disjunction between the and disjuncts, where n is the number of rows for which the formula evaluates to t. Each disjunct has n conjuncts, where m is the number of distinct propositional variables. Each conjunct includes the positive form of the proposition variable if the variable is assigned t in that row, and the negated form of the variable is assigned f in that row, the proposition in the disjunctive normal form. So this is another example here. I'm just going to go and skip over that. Here's another one, the conjunctive normal format, a compound proposition in the conjunctive normal format, C and F, if and if a conjunction, if it is a conjunction of disjunctions. Every proposition can be put in an equivalent C and F conjunctive normal form, and a conjunctive normal form can be obtained by eliminating implications, moving negations inwards, and using distributive and associative laws. And it's important in resolution theory, proving used in artificial intelligence. So if some of you either now or in the future get interested in artificial intelligence, this may be an example of something that you'll get exposed to. The compound proposition can be put in conjunctive normal form through repeated application of the logical equivalence covered earlier. So here's just a couple examples here. Once again, I'm not going to go through this in detail, but just trying to do a quick survey so you have some awareness, and go ahead and see Rosen for some details. So for propositional satisfiability, a compound proposition is satisfiable if there is an assignment of truth values to its variables that make it true. When no such assignment exists, the compound proposition is unsatisfiable. A compound proposition is unsatisfiable if and only if its negation is a tautology. Here is questions on proposition satisfiability. Here's an example here. Determine the satisfiability of the following compound propositions. We have some solutions here. I'm not going to go through these. I'm just going to let you go ahead and to be thinking about that. I'll reserve some of our precious time for other parts of what we're getting a chance to be thinking about. Here's some comments on notation. And so this is going to be used for the following example here. So now we get into an example puzzle that maybe some of you have done Sudoku type of puzzles here. So here we're showing a 9x9 grid made up of 9 3x3 subgrids known as blocks. Some of the 81 cells of the puzzle are assigned one of the numbers 1, 2, 3, 4, 5, 6, all the way up to 9. The puzzle is solved by assigning numbers to each blank cell so that every row, column, and block contains each of the 9 possible numbers. So if you've ever played this, you can see that it can get a little bit complicated. And we then want to be coming up with an approach to be satisfying this, where say if we wanted to use a computer to help us to come up with a solution, maybe using our head and using the same algorithmic approach would also be something noteworthy. So let P, I, and J denote the proposition that is true when the number n is in the cell in the ith row in the jth column. There are 9 times 9 times 9, 729 such propositions. And in the sample puzzle, P516 is true, but P5J6 is false for J equal to 2, 3, dot, 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 all the way up to 9. So to be thinking about the encoding as a satisfiability problem for each cell within a given asset P, I, J, N, when the cell in row I and column J has a given value, we assert that the given row contains every number. And here we have this notation that we got a chance to have an introduction to assert that every column contains every number. We have this notation, and Rosen or pausing the video is a beneficial way for you to get into this in a little bit more detail. We assert that each number of the 3 times 3 blocks contains every number. So we need to make this out here. And note that this is tricky, and ideas that can be helpful are found in chapter 4. We assert that no cells contain more than one number. Take the conjunction over all the values, where each variable ranges from 1 to n. And so we have that. So we're basically trying to go through an algorithm and have a way of proving it, to getting some perspective on that. And so I'm trying to hold this at a high level to give you an introduction to this material. And for some, you may really want to get into this a lot more, and that would be great. So to solve a Sudoku puzzle, we need to find an assignment of true values to the 729 variables of the form P, I, J, N that makes the conjunction of the assertions true. Those variables that are assigned T yields a solution to the puzzle. A truth table can always be used to determine the satisfiability of the compound proposition, but this is too complex even for modern computers for large problems. There has been much work on developing efficient methods for solving satisfiable problems, as many practical problems can be translated into satisfiability problems. Okay, that's going to be the end of what we're going to cover in this lecture. Hopefully you enjoy this. These are a lot of foundational topics that we'll be using as we go forward. Thank you very much.